Welcome student. Now we study about mechanical properties of fluids. In today's session we learn about Stokes law and terminal velocity. In the year 1845, Sir George Stokes stated the law which gives the viscous force acting on a spherical object falling through a viscous medium. Consider a small sphere falling through a viscous medium and Fv is the viscous force acting on it. Small r is the radius of sphere and v is the velocity through the fluid. Sir George Stokes states that the viscous force Fv acting on a small sphere falling through a viscous medium is directly proportional to the radius of sphere small r, its velocity v through the fluid, and the coefficient of viscosity eta of the fluid. That is, Fv is directly proportional to eta r into v. Experimentally, obtain the constant of proportionality is 6 pi. We putting the value of 6 pi in above equation and removing the proportionality sign, then the equation becomes Fv is equal to 6 pi eta into Rv. This is the expression for viscous force acting on a spherical object moving through a viscous medium, and it is also called as the Stokes law. The above formula Fv is equal to 6 pi neta Rv can be derived using dimensional analysis. Student, this is the one simple example based on Stokes law. A steel ball with radius 0.3 mm is falling with velocity of 2 meter per second at a time t through a tube filled with glycerin, having coefficient of viscosity 0.833 Newton second per meter square. Here we have to determine viscous force acting on the steel ball at that time. Here the given data, the radius of sphere is 0.3 mm. Convert it into the SI system, it will be the 0.3 into 10 to the power minus 3 meter. Velocity of that sphere is 2 meter per second and the coefficient of viscosity eta will be the 0.833 Newton second per meter square. We have the formula for the viscous force Fv is equal to 6 pi eta into Rv. Put the all value in the given formula and make the mathematical manipulation with the help of logarithmic table. We got it the answer. Viscous force F is equal to 9.422 into 10 to the power minus 3 Newton. Terminal velocity. Consider a spherical object falling through a viscous fluid. The force exerted by it during its downward motion are: number 1, viscous force Fv directed upward. Its magnitude goes on increasing with increase in its velocity. Number 2, gravitational force or its weight Fg directed downward. And number 3, and upthrust Fu directed upward. Here net downward force given by F is equal to Fg minus Fv plus Fu is responsible for initial increase in the velocity. From this, gravitational force and upthrust are constant while viscous force Fv increases while increase in velocity. Thus, a stage is reached when the net force F becomes zero. At this stage, Fg is equal to Fv plus Fu. After that, the downward velocity remain constant. This constant downward velocity is called terminal velocity. Obviously, now onward the viscous force Fv is also constant, and the entire discussion all necessary applied to the streamline flow only. Now we will deduce the mathematical expression for the terminal velocity. Consider a spherical object falling under the gravity through a viscous medium as shown in figure. Let the radius of sphere be small r, its mass will be the small m, and density becomes rho. Let the density of medium be sigma and its coefficient of viscosity be eta. When the sphere attains the terminal velocity, the total downward force acting on the sphere is balanced by total upward force acting on the sphere, that is, total downward force is equal to total upward force. Total downward force is weight of the sphere mg, and total upward force is combination of viscous force and by out and due to the medium. Mathematically, the weight of sphere mg is equal to 4 by 3 pi r cube rho into g is equal to total upward force 6 pi eta rv plus 4 by 3 pi r cube sigma into g. We are taking the term viscous force to one side and remaining term to other side. The equation becomes 6 pi eta rv is equal to 4 by 3 pi r cube rho g minus 4 by 3 pi r cube sigma g. From the right hand side, we take the common 4 by 3 pi r cube g. Then the equation becomes 6 pi eta rv equal to 4 by 3 pi r cube g into rho minus sigma. For finding the velocity v, we move the term 6 pi eta r towards the right hand side, and it goes to the denominator, and the equation becomes v is equal to 4 by 3 pi r cube g into rho minus sigma into 1 by 6 pi eta r. Taking the LCM towards the right hand side, and the equation becomes v is equal to 2 by 9 r square g into rho minus sigma by eta. This is the expression for the terminal velocity of the sphere. From this expression, we can also determine the formula for coefficient of viscosity. Eta is equal to 2 by 9 r square into rho minus sigma into g by v. Here v is terminal velocity, r is radius of sphere, g is acceleration due to gravity, rho is density of sphere, sigma is density of fluid and eta is coefficient of viscosity of fluid. We can see one simple example based on this formula